All right, so we looked at this at the end of class on Friday, but over the weekend you're looking at a lot more sums. I hope you had some reading that goes along with what we're going to talk about today that I asked you to read a little bit on Wednesday and on Friday both in the assignments. So we're going to be seeing these summations, and it's going to be a lot more complex looking than this. So I just want to make sure that we understand the basic components of what you see in these, what they do, and the different ways they can look and how we can make them work for us. So this one here, it says, it's got the capital sigma, the index n, where we're letting n take all the whole number values from 0 to 4. So those index values are always whole numbers, so that's the nice thing about it. So we're adding up results that we get by substituting in the whole numbers 0 through 4 into that expression. So we talked about this one. This one's a fairly straightforward one. If you just substitute in 0, you get 6, and then 11, then 16, and so forth. So that first one, the value of that sum is 80. It's a numerical sum. Each of the terms has just a numerical value. There are 5 of them, which when you look at 0 through 4, it maybe is deceptive. It looks like there's 4 things. It's 5, which that's one of the things that we're going to adjust a little bit. In order to make these index values work for us a little bit better, instead of starting with whatever we want, you can adjust sums to represent using the exact same terms added together, but make it so it's easier to see what you're doing. So if I wanted to use something that was 5 terms but started at 1 instead of 0, we decided last time that it would be 1 through 5. So if I start at 1 using whole numbers 1 through something, the something that I go through also, in addition to indicating the last number that I substitute in, it also indicates how many numbers I'm going to have to substitute in, or in other words, how many pieces to the sum there are. So that's something handy that we're going to do. We're going to start with 1. Also, that way the first number you sub in is 1, the second number you sub in is 2, and so forth. So the 5th number I'm going to sub in here would be 5. But if I do that, if I want to end up with the expression above, I have to adjust. I can't just change it to 1 through 5 instead of 0 through 4 and call it 5j plus 6, because that would then start with 11 and go up to 31. What do we need to put into the formula in place of where the variable was in order for this to give us the same result as above? Yeah, j minus 1. So, and there's nothing special about the letter n or j. Typically, for some indexes, you'll see i's or j's or m's or n's, but it could be anything. It's just whatever's indicated down below the sum. When you see that in the expression to the right of the sum, that indicates that's the part or parts that are going to be changing from one term to the next. So the rest of it would say the same. There'd be 5 times something plus 6 in each of the terms, although since it's numeric, you can easily work out what those values are. So if I go 1 through 5, using 5 times j minus 1 plus 6, that would come out exactly the same as above. The same 5 terms, result still 80. So what we're going to actually see in ours is things more like this. We're going to have function notation within our summation. As long as that function is defined someplace, we can still do the sum if it's numeric, or we could write out kind of a, like we've done before, like a dot, 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 sort of give the idea of what the pieces of the sum are going to look like. But in this one, I've got 3 times the function f evaluated at a bunch of different places. 1 plus 2k, or I let k go from 1 to 3, which is how many terms? 3. 1 through 3 is 3 terms. Again, that's the nice part of starting with 1. And k is the part within this that I'm going to change from one term to the next. So I'm going to have 3 times a function value. And those function values come from using, well, different inputs to this. I'm not using the inputs for x as 1, 2, and 3. The input of the function is going to be 3, 5, and 7. Thinking about substituting in 1 in place of that k there, I'm going to get 1 plus 2 as the input or the independent variable value that's going into function f. So notice also this 1 plus 2k. This is something you might deal with a little bit more in your next calculus class, but this 1 plus, or 2k plus 1, 1 plus 2k, notice it gives us a sequence of odd numbers here. 2 times a series of consecutive integers is going to give you all the even integers, starting with whatever the first one was, doubled. 2k, an even number, plus 1 is always going to be odd. So not particularly useful for what we're going to use sums for, but just as a side note for future reference. And if we actually go through and evaluate this, 3 times 3 squared plus 3 times 5 squared plus 3 times 7 squared, or 27 plus 75 plus 147 is 249, I believe, if I added correctly. So in any case, the adding up of the numbers is not something we're going to have to do a lot, nor are we going to talk about how to do this with shortcuts. That's all sort of pre-calculus topics or calculus 2 topics, because those are the places where you're going to use sums in general more often. For our purposes, we're going to use them for one thing, which is to be able to express accumulation due to a given rate. Because as we saw when we were writing out accumulation functions, doing one interval at a time, we ended up with horrible looking piecewise functions. But within each of those pieces, we had a series of things that were added together, most of which were kind of the same. Sums are really good for adding together and writing in short amount of, with a short amount of writing, adding together a bunch of things that are basically the same. So over the weekend, or between last time I saw you and now, you should have seen this with some question marks and also without question marks, depending on which version of it you're looking at. The quiz version has some question marks in various spots. But let's talk about, instead of a specific rate function where we had, here's a picture of like sand unloading and whatever that means, or here's a picture of a rocket basketball flying and the rate at which its height is changing. So let's just take a look at a general red curve here, an exact rate of change function. And the way that we've done approximate rate functions, picking a few values off of that, well, infinitely many really, but nice evenly spaced points, and then using that one rate value as if the function were a constant rate function, using it for a little bit, that little bit at a time that we're going to use it for is up to a maximum of, generally, delta x. So let's talk about this in terms of a general rate function, r sub f, an approximate rate function that we just generally call r without the subscript, and intervals of width delta x. Now this a is something that we didn't specify during our earlier examples. The reason was we were using it as 0. A is just this starting point, or where I start counting. Well, what happens since one particular point in time? So with our rocket basketball, it's like, well, since it took off at time 0, we measured from there onward. Or with the sand question, since time 0, since we started unloading the sand, how much sand unloaded? Or I forget what our third example was that we had, but same idea. We started from 0. We don't have to start measuring accumulation from 0. We don't have to start caring about our rate function at 0. We can always also, just like with the sum, recenter to be whatever part we're interested in. We could scale that back to be 0, but rather than do that in general with functions that I don't know what it is, r, let's just say we started a general independent variable value of a and make intervals going forward from there that are delta x units wide. So general premises, I'm going to use one rate, my rate at my exact rate function right here. I'm going to use that instead of letting my rate increase from there, because this is just a general r sub f, maybe it's decreasing in another example. I'm going to pick this rate at x equal to a and use that for delta x units until I go pick another rate and use that for delta x units. As many as it takes until I get up to whatever value of x I'm interested in. So let's say that I'm talking about a specific value of x that's somewhere between 6 and 7. So specific but general. Something between 6 and 7 with this setup. If you can see this from where you are, there's a series of red dots on the x-axis that indicate the beginning and ending of intervals. So between a, where we start, and x, where we want to find a value for, how many complete intervals are there? It's marked off with the big purple thing. Complete delta x wide intervals is x all the way past. Yeah, there's 3 all the way complete intervals, and then x is in the middle of this 4th interval. So how far is x from that a at the beginning? Well, 3 delta x's plus a little bit extra. So what I'd like to do is measure the accumulation due to that, not just how far is x away from the beginning. But if I want to measure then, let's say this is 6.75, where x is right now. And I don't have x values for where those red dots are. Just they're, this a value is something past 2, and this one's a little past 3. This one looks like 4 3/4. Whatever this delta x is, let's say x is 6.75, so we can express something kind of precisely about this. That's the only specific number on here, 6.75. All right. So what this would be finding the accumulation up to 6.75, starting from a, mystery value of a. So if I want to do that, I'm going to use that rate starting at a for a little bit, and then I'm going to use the rate at the next interval designated spot for the next delta x units. And there's going to be 3 intervals where I do that rate times delta x, an mdx sort of expression where the m is our rate function value that we're pretending is constant. So we're going to use our constant rate, plain old r, for delta x units. And then we're going to use this r for delta x units, and then this one for delta x units. And then we've just got this stray term here. So if you can see up above, this is kind of what's going on with some details left to fill in. A rate times delta x, a rate times delta x, a rate times delta x from our 3 complete intervals, or our completed intervals, the ones we've already gone past if we're at x right now. Plus, we've got this stray part at the end that's a slightly different term because we don't use that rate for as long. So in terms of summation, you can see if I can express these 3 here in terms of some way that I can describe 3 consecutive whole numbers being substituted into a rate function and end up with the expressions that I want to have here to evaluate my rates at, here, let me grab a pen here, at those 3 points. This one, I'm going to use that rate value, this rate value, and this rate value. And I'm going to use them each for delta x. So if I can find a way to express those 3 positions by making an expression where I can sub in 3 consecutive whole numbers, I can put those first 3 terms into a sum. So in general, though, if I look at those spots, the first one's definitely, before we worry about how do I put this into a summation, the first one's r of a, all right? That's the rate function at point A. By the way, if I write this as r of a, our approximate rate function evaluated at x equal to a, it's also, would you agree, r sub f of a? So if I were to put in an f here, the thing is, fake rate function at point x equal to a and exact rate function, real rate function at x equal to a, those are the same thing. They're both at that red dot. They're the same height. So either one of those, this is one specific value. This isn't a function where it's a isn't changing. A is a parameter. So whether I write r of a or r sub f of a shouldn't matter because I'm just evaluating at a spot, and that spot is a left end of an interval. So that's good to know. There's some flexibility in how to write this. But just in case you're wondering, you can write that either way. There we go. So what about for the beginning of this second interval, this spot, this first red dot past A? If each interval is delta x wide, how could I explain that position's x value? I start at A and then I go to the right by delta x. So what would be a name for this red dot's x value? A plus delta x, right? Start at A and go to the right by delta x. That's getting larger by delta x, so A plus delta x. And what about for the next red spot, the one here? It's x value, independent variable value. The left end of the third interval here, A plus 2 delta x's. Good. So when I'm looking at the first interval, my independent variable value is A. the second interval starts at a plus 1 delta x, because I've gone through one delta x interval already to be at the beginning of the second one. Or at the start of the third full interval, the x value is a plus 2 delta x, because I started at a and I went through 2 full intervals. So that a plus 2 delta x, I can think of that's the left end of the third interval or the right end of the second interval. It's both numbers. What's the piece here during the current interval? That's just another one, right? A plus 3 delta x's. That part's the same. The only part that's different about this current interval part is how long it is, because that depends on where within that current interval we are. But in any case, you can see there's a nice sequence of evenly spaced things. There should be a way to represent the input to these, the part that goes inside the function notation, inside the parentheses, indicating an independent variable value, in terms of something so that I can write it as a sum, which is what we're going to work on. So, because each of these is r of something times delta x, the rate times the length of time, the independent variable length that we use it for. So what goes inside, let me clear those dots out of the way. What goes inside, we need an expression, and I use the letter J here, and because your book uses the letter J in all its examples, so it doesn't really matter what it is, but let's say it's J. I'd like to be able to sub in J equals 1 and have it come out to A. Well, that's kind of weird. I'd like to sub in J equals 2 for my second interval and have this come out to A plus delta x. J equals 3, I want to come out to A plus 2 delta x. So each one of these is going to have an A in it. So that part's going to be the same. It doesn't have anything to do with J's. But what I'd like to change is how many delta x's are added onto that A. So in the first interval, notice there's no delta x's. In the second interval, there's 1 delta x. To represent the rate for the third interval, there's 2 delta x's. You can see it's always one number less than the interval number that I'm on. How about a j minus 1? If I have a plus some number of delta x's, as long as that's 1 less than the number that I'm substituting in, I can make the number that I'm substituting in, 1 through 3, represent also the number of interval that I'm on, the interval that I'm using this for. So the first interval, I'm going to have a plus no delta x's, if you want to think of it like that. The second interval, I'm going to have, at the beginning of that interval, the x value a plus 1 delta x. Third interval, a plus 2 delta x. Fourth interval, a plus 3 delta x, and so on and so on. So by putting this j minus 1 in there, this is just a technicality of setting this up, but once we have it set up, we're good and we can use this for all of this. Notice this is not specific to a particular rate function, a particular delta x, a particular a starting value. This works for anything. So we don't have to do this whole setup multiple times. If you can think your way through it once, then you've got it. It's going to be the same whenever we think about this sum to represent accumulation. So that's handy because it's kind of a mess. But once you get it once, and make sure you understand what the parts are for, this j minus 1 is just to adjust this so that the numbers work out the way that we want. I'd like to be able to sub in 1 and get something about the first interval. I don't want to have to substitute in 0 to get a first interval or 7 to get a first interval or something like that. If we can set this up so that the variables work the way we want them, it makes the formula a little messy, but then it's easier to understand. Substituting in 2 gives me something about a second interval. So if I put that in as the argument within my sum, then, and that's just smaller there, sorry, it's not as bold-faced anymore, but my rate evaluated at a plus j minus 1 delta x. And notice there's 2 delta x's here. It's not a delta x times delta x. This is the input to the rate function involves counting how many delta x intervals we've gone through, or this makes sure that we're only evaluating our rate function at the left end of intervals. It'll be at the ends of intervals in general, but the left end corresponds the number with the interval number. And then, so this is our m, and here's my dx, how I use that rate function. Oh, that's not the m. R of that is my m. But this is the input to my rate function, and then I multiply my rate function value times the length of time I use it for. So in terms of how do we calculate what happens, what's our rate, and how long do we use that rate for? So m dx. So the input to that is a little messy to write out. The a plus j minus 1 delta x, but the structure, once we get that down, just realize this: a plus j minus 1 delta x for any whole number value of j, well, 1 or bigger, we set it up to use 1 for the first interval and so on. That'll tell us the x value that we use in our rate for that numbered interval, whatever number you subbed in. So if I subbed in 17 for j here, not a part of this problem, but if I subbed in 17 for j, that would give me the rate at the left end of the 17th interval, and then that interval is delta x wide. If I multiply those together, I'd have how much accumulates during that 17th interval. If I substitute in j equals 184, this expression here would give me the rate in the 184th interval by finding the x value at the left end of it, finding the rate function there, and then multiplying by the width of that interval. Doesn't matter what number, whatever number I substitute in, this gives me a way to calculate the rate at the left side of that interval times the width. All right. So we've got the first part kind of set up. J equals 1 through 3, the rate function evaluated times the width of the interval. That's for the complete intervals. For the one that we're in the middle of, when we're using x equals 6.75, this is in the middle of the fourth interval. The rate at the beginning that we're going to use is r of a plus 3 delta x. The reason we can't put this in the sum is because of what it's multiplied by. It's not multiplied by delta x. We haven't gone all the way through that interval. It seems from the picture that we're in the middle of this. So for an x that's in the middle of that fourth interval, this term can't fit into the sum because it has not just the argument changing, but it has a second part changing where this could be anything between 0 and delta x. So anything between 0 and delta x, infinitely many different values this dx could have, would indicate that, oh, this sum can't fit there. So I'm just going to have to tag that on as an extra term. But notice that the piece at the beginning, that a plus 3 delta x, again, just to reiterate this part, a plus 3 delta x means I've already gone past 3 whole intervals. I'm into the fourth interval. So this 3 delta x, though, and this is going to be important for our next interval or our next example. We're going to talk about what if I don't know this is in the fourth interval? What if it's in some interval in the future? Well, this 3 here, we can figure out that it's 3 because I can count it. 1, 2, 3 whole intervals, then we're in the middle of the fourth. So when I know it's 3 whole intervals, I can put this 3 there. But it's all of the previous intervals. But this, for the current interval, the x value is the a plus however many complete intervals you have times delta x. So if that's something you know how many complete intervals you have, let's say I'm past 34 whole intervals, then be a plus 34 delta x would be the x value at the left end of the interval we're stuck in the middle of, that partial interval at the end. Why that's useful is if you don't know how many, but you know how to express how many complete intervals there are, then I can put an expression for how many complete intervals there are right here. And that's what we're going to work on next. But another symbol that we'll use just to shorten this up, the left end of the current interval, there's a function that is defined in your book for that. And it uses another function in its definition. But the left end of the current interval, not all of them, just the one that x is at the left of, is called left of x. So wherever x is, this is like a rounding style function. It rounds back. Left of x rounds you back to the beginning of the interval that x is in. So left of x, being able to describe what left of x is, depends on you knowing what a is and what delta x is. But left of x is a function where it takes on a variety of values as x grows, but the only sorts of values it has in it are distinct values. So if this were back to its animation form, left of x would be on its fourth value by now. Left of x starts at being the same as a, And then as x grows, eventually left of x suddenly jumps to here. As soon as x gets past the first full interval, left of x becomes that left end of the second interval. And as soon as x gets into the third interval, left of x becomes the value at the beginning of that third interval. So left of x is always the left end of the value that the interval that x is currently in addition to being a way to express just this a plus whole number of intervals that we've gone past times delta x. This is a way we can compute it if I can express how many whole intervals there are. But left of x is an x value. Left of x is the x value at the beginning of the interval route. So it kind of rounds back in that sense. We have a second sort of rounding function also, but this left of x gives us a short way to write that nonsense. So in this particular example, since we could count, we know that there's 3 complete intervals, and I can just write a plus 3 delta x for that input there. But in general, I'm not going to necessarily know a number for that, and it becomes really tedious to write an expression for a plus how do I compute that times delta x. So we just use this left of x function as kind of a shortcut, a helper function to help us shorten up what we intend. So this dx part, we can also write that a different way. Dx here, can you see from utilizing that left of x expression? Dx, remember, is just how far x is into this current interval. It's less than delta x. If I want to express how far it is, well, it's just whatever x is minus the left end of the interval. So this, another thing we could write here, and I'll show this on the next screen when we write everything out, but instead of writing dx here and having a second variable aside from x, because so far, well, this is a constants. Here's a variable, x. Dx would be a second variable, but I can also express dx as just, if you remember from our piecewise function, how far is x from the beginning of the interval? Well, it's, if the beginning of the interval is 6, I could do x minus 6. Maybe it's not quite 6, but it is left of x all the time. How far is x from the beginning of the interval? X minus left of x. And that will always be true no matter what interval it is, because left of x only has one value at a time. It is a function in that sense. For any value of x, there's one value of left of x. But left of x's value just takes on a series of values that are evenly spaced by whatever delta x is. All right, so let's take a look at a slightly more general example, and this is kind of finally putting together all the pieces. This takes a while to digest all of the parts, so we're going to continue looking at this. But the difference between what I'm going to ask us to do right now and what we just did is, last time it was pretend x is 6.75. So how would I express that accumulation? What if I want to express it for a general, any sort of x? In fact, it actually works even if x is less than a, but between x equals a and any current value of x, there's a couple of things that I'm going to have to worry about that I didn't need to last time. So, for instance, last time we used that picture as an exact, so it's 1, 2, 3 full intervals between 0 and, or between a and where x is, plus a little extra part. Well, I won't know that it's 3 if I'm talking about a general x. In fact, the number of complete intervals becomes a varying quantity, just like x is. If I let x take on any value, then the number of complete intervals changes as x does. So that's kind of weird. And also, knowing what left of x is, I can't pin it down as, oh, it looks like it's about 6. I'm going to have to write that in general for any x. How do I write left of x? Or how else could I write left of x? But the main parts of this that we figured out before are still the same. So I'm going to have the accumulation over all the complete intervals, however many that is, plus the accumulation in the current interval that's going on, and it's a rate used for something between 0 and delta x units. So we're still just starting at a general a and have intervals with delta x. So I could write a r of a times delta x, r of a plus delta x times delta x are of a plus 2 delta x. So this, all those r expressions are a rate in the first interval, rate in the second interval, rate in the third interval, and so on. Now, if x was small, I wouldn't have necessarily even that many terms. But just imagining a big X so I can just get the pattern down and set up my sum, we could figure out how many terms there are for any specific x value later. But the sum part of it, the pieces that are all the same from all the complete intervals, are a rate times a delta x. And those rates were all evaluated at the left end of intervals at prior values of left of x. So we have this sum. The only bit missing out of it that's different from our slightly more specific examples, I don't know quite how many intervals there are going to be. That's going to be something that changes. So we'll work on that in a minute. But the other part of this is our current interval. Well, the current interval I know is going to have wherever x is, and maybe the current interval is 0. Maybe like I'm right at a boundary point, and that's okay. Given any x value, you could figure that out later. But in general, accumulation in an interval that we're in the middle of, we could describe as r of left of x times dx. Or that dx, again, could be written as x minus left of x. And I'll put that up in a second. But the how many complete intervals, or how many completed intervals, however you want to phrase that, the ones we've already gone through. Now, if you looked ahead at some of the homework questions in the iMath AS question, homework number 6, there's some questions about how many complete intervals are there. Let's say I was starting at x equals 5 and going to x equals 100 and having intervals of width 8. How would I figure out how many 8s fit into the space between 5 and 100? Well, if I want to know, let's see, between 5 and 100, that's 95 units. How many 8s go into that? What operation do I have to do? Divide. And 95 divided by 8 is, I don't know, I should have picked something easier. Let's see, almost 12, 11 and 7/8. So how many complete intervals are there? 11 or 12? Do I get to round up? Yeah, 11 complete intervals. I don't get to round up because I haven't gone through completely 12 intervals. So the process of figuring out how many complete intervals there are, it's just, for any numbers given, it's just arithmetic. Like subtract to figure out how far between the beginning and the end you're talking about, and then divide. The weird part is you have to round down all the time. You don't just get to do regular rounding. There's an operation that goes with that, round down all the time, that you should have read about, called the floor operation. These brackets that have just the bottom brackets, that indicates to round down whatever the expression is you get inside, round it down to the nearest, or not to the nearest, round it down to an integer. So whatever x value I have here, so if I had something like, I'm going to work from, let me just use this space for a second. Let's say a is, let me not use 5 again. A is 72. X has a current value of 140. And my delta x is 9. I want to figure out then how many intervals fit between 72 and 140. Well, to figure out how many intervals there are, I need to know how much space there is, which I was trying to make this easy for myself and almost succeeded. That's 68 units between those two. So I'd have to figure out how many times 9 goes into 68. 9 times 7 is 63. 9 times 8 is too big. So what I'm doing is 140 minus 72. And you can do this with specific numbers to get the hang of it, but figure out how far apart the beginning and the end values are, this for any x, and then divide by, well, how many delta x's fit in that. So the expression that we're doing is figure out the distance between, divide it into those interval widths, and then round it down. So in this case, it'd be 7 with these mystery made-up numbers. But in general, this floor expression, x minus a over delta x, that's what we did here. X minus a gives you the total distance from left to right on the independent variable axis. Divide by delta x tells you how many chunks you can fit in there, but we want to round that number down. because I don't want it to come out like 7 4/9 or something. It tells us 7 full units and 4/9 of a unit left over, whatever this was, 5/9. So that floor expression, this number on top tells me, again, two things like we talked about. It tells me how many things I'm going to substitute into this sum, how many terms there are to the sum. It also tells me how many complete intervals there are, because if it was 1 through 7, that would mean there's 7 complete intervals, 7 terms that I'm going to have. They're all the same. 1 through x minus a over delta x floored. That means, oh, well, that top number is how many intervals there are. That's also how many terms to the sum there are, how many complete intervals there are. So that x minus a over delta x gives me a way to talk about left of x without using it if you want to. You can use left of x as an abbreviation for what's the left end of the current interval. But I also know that the left end of the current interval means I've gone through all of these complete intervals, all x minus a over delta x of them. So if there's x minus a over delta x, well, rounded down, complete intervals, number of complete intervals, then if I hadn't worked out this left of x, I could write that expression. I could write that a plus whatever, because we said this left of x, it was a plus number of completed intervals, delta x. I'm just going to abbreviate number complete, delta x. Because if I add on how many complete intervals there are, it was 1 less than the interval number I'm on, and so forth. So I could say that left of x, this function is the same as a plus this delta x. A plus how many complete intervals do I have? Times delta x. Because if I've gone through all the complete intervals, or add on the number of complete intervals delta times delta x onto my starting value, I'm at the end of my complete intervals. I'm at the beginning of my current interval. So left of x is the same as this expression. Notice that I said left of x is a function of x. This is a function of x also. Notice there's only one variable in this. There's 2 parameters, a and delta x, that show up. There's some operations, flooring, adding, dividing, etc. But x is the only variable in this. As x grows, the number of complete intervals grows, right? A and delta x are parameters we chose that we're going to keep them the same value for any one situation. We can change them and do a different problem, but they're sticking with one numerical value. A plus this expression times delta x is going to change values as x changes values, because this x growing makes more and more complete intervals, so it makes left of x grow eventually. Left of x kind of hops from value to value. It keeps the same value for a while, and then all of a sudden it jumps to the next one as soon as x grows enough. As soon as x grows by an additional delta x, then left of x hops to be 1 delta x larger than it used to be. So in any case then, I can express left of x in this way, but as you can see it's a little bit tedious. So we'll just use this shorthand notation, left of x, to indicate that. But you don't have to have this mysterious left function defined. Floor is a standard mathematical function that's built into GC and whatever. Left of x, if it's not built in, you'd have to define it, but you can. In any case, this left of x can be replaced by this expression in any situation. They're both variable expressions with x as a variable, and they also both depend on knowing parameters a and delta x, which isn't necessarily obvious from this. But in any case, looking at, clear all this nonsense off here, a little less messy to look at now. If I want to express dx, there's 2 ways I can do this, a short way and a long way. But I'd rather not have 2 different variables in my a of x function. I'd like to have just one input variable, just x. We have parameters a and delta x, but I'd like to have just x. And dx is a second variable. dx is related to x. It talks about how much x has changed. But if I want to express this dx in terms of the variable x, if you can see, it's just how far x is from the beginning of the interval, how far x is past left of x. So the short way to write it is x minus left of x. The long way to write it would be, let's not do that, x minus, parentheses, a plus x minus a over delta x floor times delta x. Ugh. So we could write it that way, but this is one of the reasons we invented this left of x function as a, it's defined for us. It's also defined in multiple calculus books the same way, but it's not a standard function that's used past a certain point. And we'll learn why, because eventually it doesn't really matter. So our whole goal in writing all of this is to be able to express accumulation the way we have as an approximate accumulation due to using this rate function. Oh, one other point, I want to make this again. I said this earlier, but since I'm evaluating this rate function just at places that are the left end of these intervals, I could use r sub f as well as r, and it has the exact same meaning because r, our fake rate function, and r sub f, the exact curved rate function, have the same values at all of those points. At these points at the beginning and ends of intervals, they have the same values. Same thing over here, r of left of x. Left of x is the end of an interval, so I could put in this f here that doesn't change its meaning at all. So there's a variety of ways we can write these. Sometimes you'll see r sub f, sometimes you'll just see r. As long as the input to the function is expressed as something that's just beginnings of intervals, those have the same meaning. So don't worry about which way it is. In fact, there's a question about that in the homework number 6, which is due a week from today. But there's other ways I could write this. R of left of x is actually just the same as plain old r of x, which is not the same as r sub f of x. I'll let you think about that one if you want to. But when I have the input as just places that are the left end of intervals, r and r sub f are the same thing, because that's how we created this function r, which means that nobody really has to know what this mystery r function is that we created. We can just talk about the regular exact rate of change function, which is nice. We don't have to explain how we put together this function, but by imagining that function in the background, these horizontal line segments, we can imagine why this works the way that it does. So this here, with, as I said, varying versions of, you might see a subscript of f on those to indicate the exact rate function. This is a way to express approximate accumulation in general for any rate function r that's devised from, and I'm going to put the f's back in there so we can talk about it, any exact rate function r. So for any given rate function, I can use that rate function from left end of intervals for a little bit. And this expression here gives me, now this isn't exact accumulation, because this is using the same rate for an interval of width delta x. So this is still approximate accumulation. But I can make it a pretty good approximation because this expresses this in general. The delta x's, if you can imagine, if I make delta x a large number, it's going to be a poor approximation. If I make delta x smaller and smaller and smaller, I don't have to rewrite this. I can still write it the exact same way. If I make delta x extremely small, what happens is for any numerical values of x I put in, that top of the sum becomes a larger something. That means I've got more intervals if I make delta x smaller. Okay. But this just becomes more exact if I make delta x smaller. And if delta x is smaller, then this part over here is going to be even smaller than delta x is. So what ends up happening is that end term at the right is going to be, if delta x is sufficiently small, that current term is going to be even smaller than you can imagine. So we can just ignore it. But this is an approximate accumulation. It's not exact, but we can make it more and more exact by picking delta x's that are smaller and smaller. And in this format, I don't have to rewrite it over and over. if we're writing things out without the sum notation and you wanted to express what happens if I make delta x equal to 0.0001 versus delta x equals 2, there's a lot more work involved in writing out all the pieces, the like thousands and thousands of pieces in piecewise format. This gives us a way to not have to write piecewise functions, which is good. Piecewise functions are not fun to write. There are a lot of parts to it. This Friday, we're going to have a quiz in class that's essentially about, do you know how to express these different parts or like make them express things? Like, let's see, the number of intervals between 0 and 48 if delta x is 17. How would you write that? Or things like that, things related to this sum. So I'll put up practice questions so you have an idea of the sorts of questions, sort of practice questions that, how do I express things with this sum? But we'll be talking about this again in class on Wednesday, doing some more things with this. And let's see, so Friday is a quiz. Your test is a week from Wednesday, so 9 days from now is your test. The test covers chapters essentially 4 and 5. Your test is going to be in 2 parts. So, one is going to be in here. You're going to do a piece of your test in recitation during next week also. And it's also related to this thing. So in recitation next week, Monday, Wednesday, or Friday, whatever your day is, you're going to have a piece of your test, short piece, like 10-minute piece. The rest of it's going to be in here, and it's not going to be focused on just that, but using this and all the other stuff about using constant rates of change when we've got more than one constant rate that we're using, whether it's 2 or 3 constant rates or a bunch, depending on how far I go in terms of x. So I'll be putting up an outline to help you start studying for the Chapter 2 test, but all of your homework is posted already. The last one is homework number 6. That sort of homework, the non-reading style homework. So look for updates today in terms of things to read, practice questions, test outline. And I will see you on Wednesday. I'm sorry? Yeah. Not today.